This is a short video about the concept of the edit distance. My name's Alan Doran. You don't need to have watched any videos before this one. It doesn't assume any real pre-existing knowledge. So, the edit distance is the minimum number of operations required to convert one string into another. Here are a couple of examples. Suppose we wanted to edit the string gold and convert it into the string old. We could do this with a single deletion. This use of one operation to transfer the first string into the second string means the edit distance from one to the other is 1. If we wanted to change gold into jailed, we would have to insert the character A and insert the character E. These two insertions mean that the edit distance between those two strings is 2. Now, what if we wanted to change gold into sold? What would the edit distance be? Well, we could delete the G and go to old, and then insert an S from old to sold, and this would leave us with an edit distance of 2. Now, if we allow, instead of just insertion and deletion, the substitution operation, then we could go directly from gold to sold in a single step. That would leave us with an edit distance of 1. If we went via the intermediate step of old using deletion and insertion as our two operations, the edit distance is 2. So the edit distance we come up with depends on the operations that are available to us when we're trying to transform one string into another. If we just use substitution, deletion and insertion, then the edit distance we get with these operations is called the Levenshtein Distance, which is named after Vladimir Levenshtein, a Russian scientist who came up with the idea in 1965. To see how we compute edit distances in general, we first need to understand a little bit of terminology. Supposing we start with a string S. This string S is made up of characters S1, S2, S3 up to Sn, where the value of n is the length of the string. So the value of n for the string caterpillar is 11. A substring of string S can be written S1 ... K. This is a substring that starts at the first character of the string S1 and goes through until Sk. K is the length of the substring. So the length of the substring CAT in caterpillar is 3. That is, S1 ... 3 is the substring cat in caterpillar. Now, these substrings are useful, it turns out, because when we're trying to compute the edit distance between two long strings, it's actually handy for us to break the problem down into smaller components by considering the substrings of the strings we're trying to compare. So that is, if we've got a string S of length n, we're interested in the substrings S1 to J, where J is anything from n-1 down to 1. That is, where the substring is of length 1 less than the original string, all the way down to a substring of length 1 character. So we might have two strings we're trying to compare, S and T. In the case of T, we write this analogously to how we wrote it for S. That is, we've got a string T of length M, and we want to look at the substrings lowercase t from 1 to K, where K goes from the length of T minus 1, that's M minus 1, all the way down to a single character of length 1. Now here we've got some more abbreviations. The edit distance from a string of length J to a string of length K can be written as we see in the top left here. And that's the distance between the substrings of J from 1 to J and the substring T of length 1 to K. Now the substring S from 1 to J is of course the full length of the string of length J. That is, we consider every substring, and the same with T. from 1 to k. Now, the edit distance from j to 0 is the number of operations it takes to convert a string of length j to a string of length nothing. That is, of course, just j deletions. If we have a string of j characters, to get it to a null string, we just delete each one of those characters. That means we have to delete j times. To go from an empty string to a string of length k, this is the third line on the slide, of course we have to do k insertions. So if we want a string of length 3 and we start with a string of length nothing, then we have to insert 3 characters. That is, we have to insert k characters in the general case. So these first two lines here, we can see e of j to 0 is just j. That's how many deletions we need to do to go from a string of length j to one of length 0. And vice versa. To go from 0 up to a string of length k, we need to do k insertions. Now, what we would like to do is write an equation, if you like, or an expression for the general case of finding the edit distance between a string of length j and one of length k. And that is the third thing down on the left, e, j, k. Now, we want to write this in terms of the lengths of the substrings of j and k. So it turns out that we can write it like you see here. The edit distance between j and k is the minimum of the 4 expressions in the big curly bracket. That is, as we'll see in a minute, it's up to us to consider all these possible operations when we're considering substrings within j and k, and to choose the one that results in the least number of operations, because you'll recall that the edit distance between two strings is the minimum number of operations required to convert one to another. Now, in the next few slides, we'll see how this large expression is used. So, as an example, we want to go from the string good to the string gold. Now we've got a table here. Across the bottom of the table, you can see the various substrings of good. Along the left-hand column, you can see the substrings of gold. And we want to know how to convert good to gold. So we're going to fill the values into these cells of the table and progressively work out what the edit distance from good to gold is. Now, each cell in the table can be read as the edit distance to go from its j value to its k value. So, for example, let's look at the first one here. To go from the empty string in the j, along the j-axis, to the empty string on the k-axis takes no effort. We don't need to do anything. Hence, the edit distance is 0, and that you can see that value filled in there. Now, to go from the empty string in j to the string g in k, we apply the second rule. That is, we say we're going from an empty string to a string of length k, and g has a string length of 1. So basically, e from 0 to k is just k, that's 1. That is, we have to do one insertion from the empty string of the character g, in this case, to come up with a destination string g. Here we do 2 insertions. We have to do an insertion from the empty string of the character g and then another one of the character o. Here we have to do 3 insertions from the empty string of g, then o, then l. And finally, in this column, we have to do 4 insertions from the empty string to get the string gold. You can see in each case we just applied the second rule that says that the edit distance between the empty string and the string of length k is the value k. So we've filled one column in this table now. Okay, now let's consider the next column. To go from g along the horizontal axis to the empty string along the vertical axis, we need to do one operation. That operation is a deletion. We have to delete G. So if we start with G and we want to get the empty string, then we do one operation, which is a deletion. And you can see here the blue arrow indicates that we've applied the first rule. That is, to go from a string of length J to the empty string, we have to do J deletions. Likewise, if we're going along the horizontal, to go from GO to the empty string, we have to do 2 deletions. To go from GOO to the empty string, we do 3 deletions. And to go from good to the empty string, we have to delete all 4 characters, so we do 4 operations, and the edit distance from good to the empty string is 4. We've now considered one row and one column of the table, and these 2 sections of the table corresponded to the simple rules, one of which goes from a string of length J to the empty string, and one which goes from the empty string to a string of length K. Now on this slide we're going to consider the cells in the table where we need to apply the more complex rule that involves, in general, the edit distance of a string of length J to another of length K, and that one is given by the minimum of the 4 rules we can see here for deletion, insertion, nothing to do, as it's written on the slide, I'll explain in a minute, and substitution. So rather than explain each of these in turn, I'm going to go through filling in values in the table and showing you how to use this rule. So the first value we're going to look at is this one here. It's the edit distance of the string G along the J axis to the string G on the K axis. Now to go from a string of length a string of length 1 that is G to another string of length 1 that is also G, we don't actually have to do anything. That is, these 2 substrings are identical. So no operation is required. Therefore the edit distance between them is 0. Now we know that. It's quite clear to us just from inspecting the source and destination strings. But let's see how the rule works. So the edit distance between a string of length J and K is the minimum of these 4 things. Now you'll see that EJK equals the minimum of EJ minus 1 K all plus 1, or EJ K minus 1 plus 1, or EJ minus 1 K minus 1, or EJ minus 1 K minus 1 all plus 1. We can compute each of these expressions on the right hand side here for the current cell we're investigating. So the current cell is at J equals 1, K equals 1. So E of J minus 1 K, that's the deletion rule, is the J to the left of the current J and the equal K. So that is, we go to the cell immediately to the left of the current cell for its value, and we see that that value is 1. That is, J equals 0 and K equals 1. Now for deletion, we have to add 1 to that value, so 1 plus 1 is 2. So the value of this first expression is 2. Now, if we consider the rule for insertion, E of J, again, this time we look at J1, that is the same column as we are currently in, and K minus 1, that's the cell down from the current cell. So that one has a value of 1 as well. It's the cell beneath us in the same column. Now we add 1 to that because that's what the insertion rule says, and 1 and 1 is 2. So again, this would have us mark a value of 2 for insertion. Now the nothing to do case says that E of JK equals E of J minus 1 K minus 1. That's the cell down and to the left of our current location. And as you can see in the table, the cell that is down and to the left of the current cell has a value of 0, which is clearly less than the values we computed before, which were both 2. So far this is the minimum of the 3 expressions out of the 4 that we've considered. Now we'll look at the last expression, the one for substitution, and it says that E of jk equals E of j minus 1 k minus 1 plus 1. So E of j minus 1 k minus 1 is the cell down and to the left of us. That's a value of 0. And we add 1 to that, gives us a value of 1. So of these four expressions, the first two had a value of 2. The third one had a value of 0. And the fourth one had a value of 1. So clearly, the third one of these, marked nothing to do, is the minimum of these four expressions, and therefore that is the value we insert in this table. Now we can understand that, as I said before, by considering all we're doing is going from a string along the j-axis, called of G, to a string along the k-axis, G, and that requires no operation, therefore the edit distance between those two strings is 0. Now let's consider the next cell up this same column. To go from G to GO, we need to do what we did before, that is nothing. We need to do nothing to go from the G to the G, but we then need to insert the letter O after our G, and that requires us to do one thing, one insertion. Therefore the edit distance between G and GO is 1, because it requires that insertion. Again, if we went through and computed all of these four expressions here, for deletion, insertion, nothing to do, and substitution, we would find that the minimum one is to do an insertion. And that has us copy the value from the current J, that is the column we are currently in, the row below us, that is the 0 immediately beneath us now in the same column, and add 1 to it, which gives us a value of 1. 0 plus 1 is 1. Therefore, we're putting 1 in the current cell. Consider the next cell. To go from G to GOL, we just copy the G across, which requires no operation, and then we insert the O as before, but now we also have to insert the L. So we're doing the same as we did to go from G to GO, but we add an extra insertion of L. And likewise, to go from G to GOLD, we copy the G across, then we insert O, insert L, and insert D. So the edit distance here requires 3 operations of edit distance 3. Now let's look at the next column. To go from GO to G, that is to go from GO along the J-axis to the substring G along the K-axis, we need to do one deletion. We delete the O. To go from GO to GO, these two substrings are identical, so we don't need to do anything. So the edit distance is 0. To go from GO to GOL, we copy the G, we copy the O, that requires no operations. But then we have to insert the character L. So the edit distance between GO and GOL is 1. And here, to go from GO to GOLD, we copy the G, we copy the O, then we insert an L, then we insert a D. So the edit distance from GO to GOLD is 2. Now at any of these cells, I can work out what value to copy in by evaluating all 4 of the expressions on the right, and working out which one has the minimum value and inserting that value into the table at the current location. Okay, next column, to go from GOO to G, we have to do how many deletions? 2. We have to delete both O's. Again, we could compute the values for all of those 4 expressions to the right of the min and work out which one had the lowest value and insert that in the table, and we would find a value of 2. And that makes sense because we're doing 2 deletions. We're deleting 2 O's from our source to get our destination string. To go from GOO to GO, we only need to delete a single character. To go from GOO to GOL, we have an edit distance of 1 because although we copy the G and the O right across, the third character, an O, needs to be substituted for an L. Goo has to become gol, so we use the 4th expression here. To go from goo to gold, we do the same as we did to go from goo to gold, but we then have to also insert the character D at the end of our expression. Last column now. To go from good to G, we do 3 deletions. To go from good to go, we do 2 deletions. To go from good to goal, we have to do 1 deletion, but we also have to replace the second O with an L. So that's an edit distance of 2 now. To go from good to gold, what do we have to do? Just 1 substitution, because the final D doesn't need to be inserted. It's already in the string good, as it is also in the string gold. All we had to do here is replace the 3rd character, that's an O in good, with an L. So that's it. The edit distance between good and gold is 1, and the operation required for interstate is a substitution. Now, across these diagonals here, you can see the steps required to transform substring from the J-axis to one in the K-axis. And that leads us right up to the right-hand corner. The first one requires no operations to go from nothing to nothing, no operations from G to G, no operations from go to go, 1 operation, that's a substitution to go from goo to GOL, and 1 operation to go from good to gold. That was the operation we did before, which was substituting the O for the L. And in this case, we're just replacing the 2 Ds directly. No operation is required, so it doesn't add to the edit distance from good to gold. Here you can see another table. This one's already been made up for you. It's to show the edit distance from sport to sort. Now in this case you can see sport has 1 more character than sort, so we actually need to do a deletion. After we've looked at S to S, we come across in sport the character P, and we've got a substring SP, which has to be converted to just an S. We have to remove the P. Now that adds 1 extra value to the edit distance. It's an insert. Now have a careful look at this table and the cells I've highlighted. Have a go and see if you can build it yourself. Maybe pause this video and see if you can track through all of the edits required. Maybe write the rules from the previous slide out on a piece of paper and see if you can apply them. Now, I don't pretend that this video has been good enough for you to understand edit distance completely. There are plenty of examples we haven't been able to do in the video. On top of that, video may not be the best way to explain this. Sit down with your friends, have a go over the example that I've given, maybe make up 2 words of your own that have 1 substitution but equal length required to edit one from the other, and see how you go. Still, if you get nothing else from this video, make sure you understand that the edit distance is the minimum number of operations required to convert 1 string into another, and that this is computed by considering substrings of the initial strings incrementally constructing 1 complete string from another. Thanks for watching.